All right, so now we'll move on to the next part of our lesson. So we're going to talk about objects moving in vertical circle. So in the previous section, we were discussing about horizontal circular motion, right? So basically, we learned two main principles, right? When we were solving horizontal circles, there were only two principles. Basically, the object is in vertical equilibrium and you apply F equal ma towards the center. All right, so now in vertical circle, the first thing is you need to understand the difference between a horizontal circular motion and a vertical circular motion. So basically, vertical circular motion is, I mean, a straightforward example, like maybe thinking of moving the movement in a Ferris wheel, because you can see that your height is changing, right? Basically, at one point, you are at the lowest level on the ground. Again, after some time, you are at the highest level from the ground, right? So basically, it's a vertical motion because your height is changing. As you can see, vertically, you are not in equilibrium, right? So when we were doing horizontal circular motion, regardless how the object is moving, the object was vertically always in the same height level. The height level never changed, the vertical height, right? So in vertical circular motion, the height level is constantly changing. The height will always change because always you're moving, because you're moving, there is a vertical movement involved. Okay, so in the vertical circular motion, you have a height change. So basically, you don't have vertical equilibrium here. All right, so then what are the equations and what are the techniques we use? So over here in vertical circular motion, also there are two main rules you need to use. Okay, so the first one for motion in vertical circle of radius r. Okay, so if you have a vertical circular motion with radius r, the components of the acceleration are r omega square or v square over r. This we know, this is centripetal acceleration. So basically, in other words, you can definitely apply F equal ma towards the center. F equal ma towards the center is always valid for circular motion. Regardless whether it's horizontal or vertical, you can always apply F equal ma, but it needs to be applied towards the center. So first you need to draw a proper force diagram. You mark all the forces and then you can apply F equal ma towards the center. So that's one rule that you can definitely apply. Okay, so what about the other rule? I think you can definitely understand that vertical equilibrium does not work here. Okay, the object is moving vertically. So there is definitely, no, we don't have vertical equilibrium. So what's the other rule we use? So over here, the other rule that we use is we use the work energy principle. Okay, so basically in this, when this circular motion, I think you can see, if there's no external force, basically most of the time, this is going to be, the circular motion will not have any external forces. So we are going to use the fact that energy is conserved. Okay, so force directed towards the center of the circle is perpendicular to the direction of the motion of the particle. Okay, so it does not work. So if the only other force acting on the particle is gravity, then it follows that the sum of the kinetic energy and potential energy of the particle will be constant. Basically, in other words, if they are saying you use what they are asking you to use the law of conservation of energy. Okay, so those are the two main principles you need to use. Okay, so first one, I think first you will have to always use the law of conservation of energy. Okay, so when it comes to these vertical circular motions, the first is, first you should use the law of conservation of energy. And then the second step is you apply F equal ma towards the center. So you need the force diagram to do this. So these are the two main principles. Okay, so now let's go into sums and let's see how to practically use these principles. All right, so we'll move to exercise 4D, question number 1. So they say whenever numerical value of G is required, you should take G as 9.8. All right, so question number 1, a particle of mass 0.6 kilogram is attached to end A of a light rod, AB of length 0.5. So you have a light rod, okay, and at the end of the rod, you have a mass 0.6 kilograms attached. The rod is free to rotate in a vertical plane about B. So the rod length is AB and the rod is rotating around the point B. The particle is held at rest with AB horizontal. Okay, so how does this start? The rod is initially horizontal. So these are really important things. Okay, so guys, read the question and kind of try to visualize what's happening. You have a rod The two ends are AB. At the end A, you have a particle of mass 0.6 kilogram attached. The end B is kind of like pivoted. So it's fixed because end B is where it's free to rotate. Okay, and they say initially the particle is held at rest with AB horizontal. So when you're initially drawing this, you should draw it like this. Can you see? So this is the rod. So this is the point B. So we'll say it's pivoted around B, right? And this is particle A. This is particle A. Okay, so okay. So initially it's horizontal, as you can see. Okay, remember it's fixed around B. Okay, so the particle, the point B is not moving anywhere. Point B is fixed. Okay, so the particle is released. Calculate the speed of the particle as it passes through the lowest point of the path. Okay, so guys, now it's currently held horizontally. Okay, it's currently being held horizontally from the point B. So point B is fixed. And then when you release it, now at this point, you have to keep holding it, right? Because it, because it's free to move around B. So you are holding it and then you are releasing. You are releasing the particle A. So guys, when you release particle A, what happens? I think you can see this. When you release, it starts to fall down. Particle A starts moving down, isn't it? Can you guys see the movement? So you start moving down. Okay, so you start moving down in a following the circular path. Can you guys see? So this is when it is directly vertical down, and then it will just continue in the circular path. Can you see, guys? So it will follow in the circular path. Can you see? Okay, so pivoting around B, so the rod will, just fall like this. So it will go like this. Can you guys see what's happening? The movement. Okay, so it will fall. So B will be, you're keeping the point B is pivoted, so that doesn't move. So around the point B, particle A, the rod and particle A will start to move. Is that clear? I hope this diagram makes sense to you, right? All right, so now let's go to I just drew this part just to show you. Okay, so now we'll go to the part we need to draw. The particle is released. Calculate the speed of the particle as it passes through the lowest point on the path. So obviously when it comes to the circular motion, what's the lowest point? The lowest point of the circular motion is obviously vertically directly below B. Vertically below B, that's where you have okay, so this is the lowest point on the path. Agreed? So initial speed is 0. So I don't know the speed over here. Okay, so it will definitely achieve some speed, right? It will definitely achieve some speed here. So they're asking you to find this speed. At the lowest point, what's the speed this particle achieves? Okay, so let's find it. So how do we do this? The main principle we use here is we use, as I told you, the law of conservation of energy. First, we'll use the law of conservation of energy to find the speed. All right, guys. So now we'll go to use conservation of energy. So when it comes to energy in circular motion, you only have to deal with two types of energy. Okay. So you have kinetic energy and you have potential energy. So that's it. Okay, that's it. You only have to deal with kinetic energy and potential energy. All right. So over here, you can see at the starting point at point A, you don't have kinetic energy, but when you come to point B, you can see that it has gained some amount of kinetic energy, right? So basically, you could say maybe initial energy equals final energy. So anything works. Or you could say the kinetic energy gained. I think you can say because because you're gaining speed, you can say kinetic energy gain. And that should be equal as you can see you're moving downwards. So potential energy is lost. So any of these things work. Okay, so you could say KE gain is equal to the PE loss. Okay, any of these things work. Or you can say, initial energy, the energy you have at A should be equal to the energy that you have at B. So use any of these concepts, it's fine. Okay, so initial energy is equal to final because energy is conserved. So initially the energy we have. So if you're using initial energy final, you need to set a GP 0 level. So as you can see, I set this as the GP 0, the lowest point. I have set the lowest point as GP 0 level. So in that case, when the height is measured above the GP 0 level, I mean, you have a GP. So at the point A, you can see there is no kinetic energy. There is no kinetic energy, but at the point A, we have potential energy. So we have at point A, we have potential energy. Okay, and when you come to point B, guys, over in point A, we only have potential energy. So when you come to point B, you can see you are at the ground level. So there is no potential energy, but you have kinetic energy because you have achieved a certain speed. Okay, so basically, once again, the same story. As you can see, the potential energy loss is equal to KE gain. Okay, whichever the one you use, it's absolutely the same. The potential energy is mgh, kinetic energy is half mv square. You can remove the m is the mass that can be removed. Guys, what about the height? Now, when we talk about the height here, height should represent the vertical height. So basically, the vertical height the object has displaced. So what about the vertical height? As you can see, the vertical height is the radius, isn't it? So how much is the radius? 0.5 meters. Right, the length of the rod is 0.5. The length of the rod 0.5 becomes the height, as you can see, the vertical height. So G into height is 0.5 equals half into V square. So making V the subject, you get here 2 into G into 0.5 equal V square. So 2 into half, it's actually 1, right? 2 into 0.5 is 1. So this is basically V square equal G. So V equals to root G. And you can give the answer correct to 3SF. Okay, so when you use G as 9.8 and take the square root of 9.8, you can get a long decimal. Yeah, so correct to 3SF, 3.13 meters per second. Yeah, so this is correct to 3SF. Yeah, okay, so that's 3SF. And then the next one, part B, the tension in the rod at this point. So they're asking you to find the tension in the rod at this point. At this point means what? At this point means the lowest point. Okay, so at the lowest point, what's the tension? So how do you find the tension? As I told you, there are only two principles. You use conservation of energy and you use F equal ma towards the center. So basically at this point, at the lowest point, we will be now be considering F equals ma. Okay, so shall we mark the forces? Okay, at the lowest point, what are the forces we have? So guys, you have, I mean, at that instant, at the point when the rod reaches the lowest point, mark all the forces. So first thing we have is what? Definitely we have the weight, right? So you can see the object, have they given the mass? Mass 0.6. Okay, I didn't use the mass value here because it cancelled out, but over here we need the weight. Okay, so mass 0.6, which means weight is 0.6 G acting vertically downward. All right, and then because it's a rod and you can see they want the tension. So tension is acting directly vertically up. Can you guys see? Tension on the rod is acting on the rod, isn't it? So it's acting upwards. So that's it. These are the only two forces we have. We do not have any other normal reaction or friction. There's no such thing here, right? So we only have the tension and the weight. All right. So the rule is you apply what? In circular motion, you apply F equal ma towards the center. So over when you are at the bottom point, the center is directly up. So you need to apply F equal ma upwards because we need to apply F equal ma always towards the center. So depending on the position. Okay, so in vertical circular motion, F equal ma on the circle, it definitely depends on the place where the particle is. Okay, centripetal force. So here F represents the centripetal force. So that is the, as I told you, centripetal force is not a force on its own. Okay, centripetal force is not, there is no force called directly called centripetal force. It's centripetal force is what's acting over here, like the tension, weight, so all of these combined. The resultant force is what makes the centripetal force, basically the force that's acting towards the center. Okay, so you don't there is no single force called centripetal force. So this is the force diagram. And then when you apply F equal ma towards the center, so upwards towards the center you have tension. Towards the center, you have the tension, and then you can see 0.6 G is away from the center. So that should be a negative. He is acting towards the center, 0.6 G is acting away from the center. Okay, equals mass. So mass is 0.6 into acceleration. So when it comes to centripetal acceleration, we have two equations. Either we use v square over r or r omega square. So since we know the v value, I think you can see we know the v at this point. Okay, so bear in mind the v value we found in the previous part is only applicable at the lowest point. Any other place, the v will change. Okay, so we are at the lowest point and we know the v value. So we'll use v square over r. All right, so t minus 0.6 g equals m into v square. So v square is v is root g, right? So v square is g, right? Guys, can you see over here? V square is actually equal to g when 2.5 cancels out. So I'll directly use don't go to use 3.13 square. Okay, so please don't use 3.13 square because this is the answer given to correct to 3SF. So when you're using the part A answer in part B, try to use the exact answer. Yeah, so this is v square is g over radius is 0.5 and you're supposed to make t the subject. So t equals 0.6 into g is 9.8 divided by 0.5. Take the minus 0.6g to the other side. Plus 0.6g. Plus 0.6 into 9.8. So you can give the whole thing in the cal. And you can get the answer for the tension. Right? So I think you get 17.64, right? Yeah, 17.64. Okay, so this becomes 17.64, but you need to, when you use g as 9.8, make sure to give the answer in 3 steps. So it's going to be 17.6 Newton corrected to 3 steps. Okay, so make sure you mention that you are correcting to 3 steps. All right, so these are the, this is basically how the question works. So as I told you, only two principles to use, conservation of energy and F equal ma towards the center. So you need to use it properly. It's quite simple. But we need to do more questions, but there are more variations, right? So we'll move into more different types of variations and see how this goes. All right, so moving on to question number 2. A particle of mass 0.4 kilogram is attached to end A of a light rod AB of length 0.3. The rod is free to rotate in a vertical plane about B. Okay, so there are some similarities now between question number 1 and question number 2. So particle is attached to end A and it's rotating around B. The particle is held at rest with A vertically above B. So guys, this is important. Okay, so if you try to do question number 2 in the exact same way I did question number 1, I think you can see that you will not get it correct now. Okay, so question number 2, the placing is different because the way the initial setup is now different than the previous one. Okay, the particle is held at rest with A vertically above B. The rod is slightly displaced. Okay, so that the particle moves in a vertical circle. Calculate the speed of the particle as it passes through the lowest point of the path. All right, so first thing you should do is, draw the initial setup. So what's the initial setup? You have the rod AB and initially A vertically above B means the rod is vertical. Can you guys see? So you can draw the rod with one line. That's perfectly fine. Okay, so I think some of you had asked me, do we need to draw with 2 lines? So you could draw the rod with just 1 line. Okay, that's perfectly fine. Okay, okay, that's fine. Okay, so this is point A and this is the center, that's point B. All right, so you're slightly displacing it. So you're slightly displacing it. So let's say we displace it to this side. Okay, so if you displace it to this side, and since it's a rod, you can understand it's not a string. So this is not going to collapse. And then it's not going to collapse. So it's a rod. So this will keep this radius and move in the circular path. Agreed? It will keep the radius and move in a circular path. So can you guys see? So it will keep the radius and move in a circular path. And then it will come directly down. Okay, so we are concerned about the point when it comes directly down. Okay, so the speed at this point, we do not know the speed. So let's mark it as V. Initial speed is 0, right? Why do I say initial speed is 0? Because they say it's slightly displaced. The particle is held at rest, okay? And the rod is slightly displaced means you're not giving it any velocity. You're not given, there's no initial velocity given. So slightly you displace, and the slight displacement will make this move around. Is that okay, guys? And you can understand that this particle will move like this, right? Can you see? Moving down, moving down, moving until it comes here. Okay, so you guys can see how the movement is happening, right? So I'll just erase here the extra diagrams because they're not required. All right, so okay. Okay, so they're asking us the speed of the particle. Okay, calculate the speed of the particle as it passes through the lowest point of the path. So when you're going through the lowest point, what's the speed? Okay, so again, we use the same concept. What are they? We use conservation of energy. So if you use conservation of energy, I'll be considering the lowest point as my GP 0 level. Okay, so if you are going with the GP 0 level, you mark it. Otherwise, you don't need to mark a GP 0 level. If you are going with the energy rule, like the initial energy, GPE loss equal KE gain, you don't need to mark a GP 0 level, okay? Yeah, and another question you might have is, do we need to draw the object in this way? Can't we draw it to the other side? Yes, you can draw it to the other side. So you could say the displacement, slight displacement is given to the other side and draw the part over here. So it doesn't matter. So I just chose this side. So if you wanted, you could have gone to the other side. Okay, just one of the two sides, only one of the two sides. Okay. All right. So let's go mark the fourth. Let's go with the rule. So conservation of energy. Initial energy is equal to final energy. So guys, initially, I think you can see initial energy. Initial energy is equal final. Or you can say the GPE loss is equal to KE gain. That's exactly what you're getting here, because at the top point, there's no kinetic energy. At the top, you have potential energy, which when you come down, you're going to lose. Do you agree? So at the top point, you have potential energy, or you can say GPE. And this GPE is what you're going to lose. You completely lose it, right? Because from here to here, it's completely gone. And that's at the bottom point, you can see you don't have any height. So there's no GPE. At the bottom, you have gained a certain velocity. So basically, you have a kinetic energy. So this is the word GP loss, KE gain. So these two are equal to each other, right? Okay, so GPE is mgh. Kinetic energy is half mv square. So directly the m can be removed. Okay, so let's input the value of g into height. So what about the height? I told you when it comes to the height should be the vertical height. So start from the point where we start. Now we are using the conservation of energy from A to the lowest point, right? We are using the conservation of energy principle from point A, the highest, to the lowest point. So basically this height is, guys, what's the vertical height here? We need the radius. So what's the radius? Okay, so they say here radius, length 0.3, right? Yeah. 0.3 meter radius, another 0.3 meter radius. So basically the full length is the diameter, yes. Okay, so 0.6. As you can see, the vertical height is 0.6 equals half into V square. So guys, take the half to the other side. So 2 into G into 0.6. First, we'll get the answer in terms of, it's better to have the V square answer exact first, because we'll most of the time probably be using the V square answer again. So V square is 1.2 G. So V equals to root 1.2 G. Is that okay? So that's the exact value. Yeah, so I'll keep it as root 1.2 G. And how much is the root value? So when you root the answer, 1.2 into 9.8 square root, you get 3.429. It goes on 3.42928. Yeah, so 3.43 meters per second. So make sure you mention that it is given to 3SF. Okay. All right. So then the next one. Part B, the tension in the rod at this point. So how do you find the tension at this point? I told you to with the tension, you have to consider centripetal force. Okay, so centripetal force is the force basically acting towards the center. So what are the forces we have over here? So at the lowest point, what are the forces that you need to know? So basically, you definitely have the weight acting always vertically down. And what was the mass? Mass is 0.4. And so this is the tension. Okay, so it's the same two forces, right? So tension is 0.6 G. So basically, if you apply F equal MA towards center, so upwards, right? The center, in this case, when you have the lowest point, center is directly up. So you get here T minus 0.4 G equal mass is 0.4. Acceleration, we will use V square over R. Okay. So T minus 0.4 G equals 0.4 into V square. V square is 1.2 G. Can you see, guys? V square is 1.2 G over radius is 0.3. Okay, so let's get the T value. So yeah, so we come to this point, T equals 0.4 into 1.2 G over 0.3 plus 0.4 G. Can you see, guys? Yeah, so that's it, right? So this is the value. This is okay. Yeah, so if you type this in the cal, make sure you give G as 9.8. Okay, so 9.8 is the G value you should give in M1, M2, M3. So type the whole thing in the cal. 0.4 into 1.2 into 9.8 divided by 0.3 plus 0.4 into 9.8. And I think you get directly the answer comes with directly in 3SF. So 19.6 newtons, right? So in the cal. So you don't have to correct it to 3SF. It already comes to 3SF. So this is it. 19.6 Newton is the tension acting in the rod. Okay, so I hope this part is clear with everyone now. Okay, so guys, we'll move on to question number 7. A particle A of mass 1.5 kilogram is attached to one end of a light inextensible string of length 2 meters. The other end of the string is attached to a fixed point B. So guys, over here now, bear in mind, we are working with a string, okay, not with a rod. So these words are important, okay, rod and string, okay. Okay, the particle is hanging in equilibrium when it is set in motion with a horizontal speed of u meters per second. So can you see the particle is hanging in equilibrium? So at the beginning, I think you can see if it's a string, okay, you need to understand the string doesn't have the same support as the rod. The string doesn't have the same support as the rod. So the string is hanging down. So this is where it is initially. Okay, so this is where the string is initially, it's hanging down. This the particle is hanging in equilibrium when it's in motion with a horizontal speed of u. So you're giving an initial speed. Can you see they say initially they give a speed of u. Find an expression for the tension in the string when it is at an angle theta to the downward vertical through B. Okay, so they're asking you to get an expression for the tension when the particle is at this point. Okay, so guys, we're going to use the exact same principles that we used before. The principles are exactly the same. Just that the position. So right now we are not having the particle is not about, I mean, at this point you can see it's in some kind of like a general position. So we had to work with the theta angle now. Okay. Okay. All right. So the first thing we'll do here is, okay, the first thing we'll do here is we'll get the expression, to get the expression for the tension. You know, the first thing we should do is apply the law of conservation of energy. All right, so we'll apply the law of conservation of energy. So let's say at the point A, the velocity is V. Okay, so at point A, the velocity is V. Okay, so let's apply the law of conservation of energy. So by the law of conservation of energy, what happens?
If you're telling me that they're apparently they're done.
Okay, so we're going to apply the law of conservation of energy. Guys, I hope you guys are reading this question. You need to read this properly to understand the setup, okay? Okay, so because I can see that you guys might have a confusion. The particle is hanging in equilibrium. That's over here. and you set in motion with a horizontal speed u. So when you set it in motion, it's going to move in this path. Can you guys see? So it's going to move in this path, and then we are particularly interested at the position, I mean at the point where the particle has turned an angle theta. Okay, so when you're at this position, they're asking you to find the tension. All right, first things first, let's apply the law of conservation of energy. So initial energy is equal to final. So if I consider the initial energy here, you can see that I'll set the lowest point as GP0 level. So at the bottom point, we have kinetic energy. I mean, there's no we have kinetic energy, right? At the bottom point, we have kinetic energy. So basically that kinetic energy you'll be losing completely. The kinetic energy over here at the point A, you have, I think, So wait, we have a kinetic energy in both the places, right? So at the very bottom point, you have an initial KE. Okay, there's no potential energy, but at the point A, okay, at this point over here, you can see we still have a kinetic energy. So I'll say it's the final KE, and you also have a potential energy, the GPE. Can you guys see? So basically some part of the kinetic energy will be lost, but not completely lost, because you don't have, the velocity doesn't become zero for the kinetic energy to completely lose. So initial kinetic energy half mu square. Okay, you could bring the final KE here as a subtraction and write KE loss. Okay, that's perfectly fine. Final kinetic energy half mv square. Okay, plus GPE. GPE is mgh. Now over here, this is the place where you need to be cautious. Why? Because you need to write the height. And how do we write the height? How do we write the height? Okay, so the length is 2 meters. Okay, so this length is 2 meters. But the thing is, I need the vertical height, right? So how do I get the vertical height? You guys look. So the particle starts from here, ends up in here. I think you can see the vertical height is this. The vertical height is this, right? So how do we find this vertical height? All right, look. So you can see that this length is 2 meters. That's the radius. And again, you can see AB is also once again the same 2 meters, right? That's also the same 2 meters. So you can see, guys, this is, you can resolve, right? So this length, guys, can you see? Let me erase this part. You can see, guys, that this length is 2 cos theta. Can you see? So this length is 2 cos theta. Can you see? This length is 2 sin theta. I'm taking it towards the angle. The thing is, I'm interested in this vertical height, the value h. So how do I get the h value? How do I get the h value? So you can see that the full length is 2. Okay, so from this complete radius 2, if you subtract the 2 cos theta, can you see that you are getting the height? So the height h is going to be equal to radius 2 minus 2 cos theta. Is that clear, guys? Not to, you need to subtract this length so that you get the remaining length. Is that clear? So the yellow color length is from the 2 meter, you subtract the 2 cos theta. Great. I hope you guys can see this 2 cos theta. This is not 2 sin theta. Okay, because the angle, when you're resolving towards the angle, it's cos this, the horizontal length is 2 sin theta. So I don't need the horizontal length. I need the vertical. Vertical length in this case is 2 cos theta. Okay. So guys, don't make sure you understand that part properly. All right, so let's give the height. Okay, so let me input the height now. First, I'll cut off. M is common to every person. All the 3 terms have an M, so I'll remove half u square equal half v square plus g times height. So inside brackets, I'll use the height as 2 minus 2 cos theta. Guys, can you see 2 minus 2 cos theta? Okay, and then I'll make v square the subject here. Okay, I'll make v square subject. So I want to first find the speed at this point. I'll multiply the whole equation by 2 to get rid of the half. Okay, so it's the whole equation. So I get here u square equal v square plus 2g times 2 minus 2 cos theta. So u square equal v square plus 2g into 2 is 4g minus 2g into 2 is 4g cos theta. Okay, so we have here v square equal u square minus 4g plus 4g cos theta. Okay, is that okay? All right, so I'll keep it at this point. Now the question is not to find the V. They're asking us to find the tension, right? So we are supposed to find the tension. So to find the tension, we will now use F equal MA towards the center. At this point, you will use F equal MA towards the center. Okay, so let me go back to my diagram. Okay, now the next thing you'll do here is mark all the forces. So now this is really important. Pay attention to the force diagram because the force diagram is what's going to determine whether you're getting the answer correctly. Okay, look, what are the forces acting at this point over here? At this point over here, what are the forces that are acting? Okay, guys, number one, you have the weight. Always the weight is acting vertically down, isn't it? Always the weight acts vertically down. So is there a particular weight they have given us? Mass 1.5 g, a particle A of mass 1.5 kilogram. Okay, so this is 1.5 kilograms, which means the weight is 1.5 g. Are you with me? Okay, so what are the other forces you have? The weight is acting always vertically downwards, and since you have a string, you know the string has a tension. The tension is acting like this, right? On the string, so this is the tension. So guys, over here, you can see now I'm trying to use F equal limit towards the center. So we can see tension is direct now. The center of the circular motion is B. The center of our circular motion is B. So when you apply F equal limit towards the center is B. And you can see the tension is already directly, it's directed towards the center. That's fine. But what about the 1.5 G? You can see 1.5 G is not in the proper direction that we require, right? So we need to fix that. So how do we do that? How do I do that? So you can see I'm drawing the lines. Okay, I'm kind of like drawing the lines over here because I need to replicate the theta angle. Okay, I'm going to resolve the 1.5 G. So guys, if you look over here, I hope you guys can see that this theta angle comes here. Can you see this theta angle over here comes here through corresponding angles? Can you see corresponding angles over here? You can use basic geometry or you could use alternate angles and get theta over here and then use vertically opposite and get. I think you can see these two thetas are alternate. Can you see? And then this theta comes here over here through vertically opposite angles. So this is completely geometry. Can you see? And now you can see I have the ability to resolve the 1.5 G. So I can resolve 1.5 G in this way. So you can see that I get a 1.5 G cos theta directed away from the center. Can you see? Because I need to have the forces resolved, like, towards the center, away from the center, it needs to be resolved. So you can see 1.5 G cos theta is directed away from the center. 1.5 G sin theta is not required. We don't need to work with that because we are only concerned F equal MA towards the center. So towards the center, we have the tension and 1.5 G cos theta is also in the center direction, but not towards, away from the center. Can you guys see? So this is all you require. So now what we need to do here is we will apply F equal MA. So I will apply F equal MA towards the center. So towards the center, you have the tension. Okay, towards the center, you have the tension. Okay, so towards the center, we have tension minus 1.5 G cos theta equals mass into acceleration. Mass is 1.5 kilogram. Acceleration is, guys, centripetal acceleration, V square over R, or you can even use R omega square. But I'm going to go with V square over R. Why? Because you can see I already know V square. We already have an expression for V square. Can you see? In terms of theta, we already have an expression. So write the answer, T minus 1.5 G cos theta equals 1.5. I'll bring the R down here. Is that okay? Radius was how much? 2 meters. 2 meters times, guys, inside brackets, let's use the V square value. V square is U square minus 4G plus 4G cos theta. u square minus 4g plus 4g cos theta. Guys, can you see what I've done over here? I replaced the v square from the energy equation into this value over here. And now you're supposed to make what? Be the subject. Okay, so let's expand the bracket. T minus 1.5 g cos theta. So 1.5 over 2. Guys, we'll type this in the cal, right? Okay, so 1.5 over 2 is 3 over 4. So guys, 3 over 4 into u square minus 3 over 4 into 4g plus 3 over 4 into 4g cos theta. All right, so P equals 3 over 4 u square minus 3g plus 3g cos theta plus 1.5g cos theta. So we can simplify this, right? So how much is it? 3 over 4 u square minus 3g plus 3g cos theta. Yeah, so plus, guys, we can add these two guys together, right? 3g cos theta plus 1.5 is 4.5g cos theta. 4.5g cos theta is a 4.5 is another way of saying 9 over 2. 9 over 2g cos theta. So you could maybe keep the whole thing in decimals or keep the whole thing in fractions. Okay, but anyway, I give the answer in terms of u, in terms of g, and in terms of cos theta. So that's really important. Okay, guys. And so yeah, so this is the answer for the tension. Just to clarify one more thing over here again, just with the weight, I really want you to understand over here, the tension is directed towards the center. So there is no need to resolve the tension. Remember, any force who is not directed towards the center, if the line of action of that force doesn't go through the center, that's where you need to resolve. Now over here, the weight, the line of action of the weight, you can see it doesn't go through B. And that's why weight needed to be resolved. Okay. So tension didn't need to be resolved because of that. Because the line of action of the tension already goes through the point, the center of the circle. All right. So those are some important things you need to understand. All right. Okay. So we'll move on to the next part, part B. Okay. So in part B, guys, they say to find the minimum value of U for which the particle will perform a complete circle. Okay, so they are asking the minimum value of u. Now, u is the initial speed, right? So they are asking for the smallest u value, which will make this particle perform a complete circle. Okay, so how do we get a complete circle? Now, what's the requirement to perform a complete circle? So guys, over here, I think you need to understand when you're now, basically, first thing is, this is, you're working with a light inextensible string. Okay. So you're working with a light inextensible string. So when you're working with a string, I think you need to understand that the point that the particle or the string will have the most difficulty in passing is where? Is the topmost point, right? So if it can pass this topmost point, then definitely the other part will definitely work with gravity, right? So it's the hardest part to go through is the topmost part. Okay, so then basically, when they ask you to find the requirement, or basically the minimum value of u for which the particle will perform a complete circle, for the complete circle, it doesn't mean that you, I mean, you come back to this point, but you need to understand that in circular motion, in vertical circular motion, the point that you need to always check is the topmost point. So if the particle can pass through the top point, then definitely it will perform the complete circle. Okay, so what's the requirement to go through the very top? Okay, so these requirements are given to you in your textbook. So you can see I have taken it out over here. So they have given requirements for 3 types of objects, for the light rod and for the wire and for the inextensible string. So we will move to the third point. So this is the one that we require in this sum. So they say a particle attached to a light inextensible string will perform complete vertical circles if the tension, guys, this is important, if the tension in the string is greater than 0 at the top of the circle. Can you see? So this is what you require. So in order to perform the complete vertical circle by a light inextensible string. So we are working with a light inextensible string now, okay? So with a light inextensible string, the requirement to go through the very top of the circle is what? Is that you have the tension. The tension in the string must be greater than 0. So this means that the speed of the particle when it reaches the top of the circle must be large enough to keep the string taut at the top of the circle. So basically, definitely when you're at the top of the circle, there should be some kind of a speed. The speed can't be reaching 0. So there should be a speed which is good enough to keep the string taut. Okay. And this is the requirement and you need to remember. I think you can see the requirements are changing for a rod. I think you can see if you are working with a rod to perform a complete vertical circle, it's not the tension. In a rod, it's the speed that should be bigger than 0. I hope you guys can understand why for rod they are concerned with the speed, but why for the string they are concerned with the tension. I think you need to understand in a rod, you do not have the problem where the rod becomes slack, right? The rod doesn't become slack because the rod is a rigid object. So in a rod, to pass the topmost point, it's the speed that affects. If the speed is bigger than 0, the rod will pass through the top. Okay, but in a string, it's not only the speed. The speed itself is not the only factor. It's the tension, because if the tension is not there, the string will become slack and the particle will start falling down. It won't perform the complete circular motion. So in order to perform the complete circular motion, the tension should be good enough. The tension should be large. The tension should not be 0. The tension must be larger than 0. And they are saying that's what they say. This means the speed of the particle when it reaches the top of the circle must be large enough to keep the string taut. So we don't need to worry about we don't need to find the velocity though, but it should be good enough to keep the string taut. It should be good enough to keep the tension positive. Okay. All right, so we'll go with this point. So we need the third point at this case. So in part B, so we need to perform a complete vertical circle. Okay, what's the requirement? Tension. Okay, at the top, the tension must be greater than 0. So guys, what's happening at the top? I want one more thing. At the top, what would be the theta value? The thing is, I need to get that. Now you can see we are measuring theta from the downward vertical. Can you guys see? We are measuring theta from the downward vertical. So when the particle is at the very top, what is the theta value, guys? So guys, when the particle reaches the top, I think you can see the angle turned. Now, currently the angle theta is measured from the downward vertical. So when this particle moves up over here, you can see the theta changes, right? So this becomes a new theta. So when it comes over here, this is the new theta. So when it comes to the very top, you can see that this full angle, the 180, theta becomes 180. Can you guys see? I hope you guys can understand that. So theta becomes 180. Okay, so at the very top, okay, so at the bottom over here, theta is 0. At the very top, theta becomes pi radian, so 180 degrees. So that's all you need here. So at the top, okay, to perform complete vertical circles at the top, or at the top in the sense when in our case when theta is 180. Okay, so if you're going with the if you use 180 degrees, if you're Kelvin degree mode, you can use theta is pi if you and use the Kelvin radian mode. Okay, I'll go with pi. Maybe it's better to go with radian. Does not make a difference though, because you don't have any other theta term outside on its own. So if you're with the Kelvin degree mode, 180 should be good enough, or with the Kelvin radian mode, pi should be okay. Okay, so I'll go with this. Tension is 3/4 u square minus 3g plus 9/2g cos theta, 9/2g cos pi. So this is the tension, right? And this tension must be greater than 0. The tension must be greater than 0. And we need to find the minimum value of u, right? All right. So let's make it the subject 3 over 4 u square minus 3g plus 9 over 2g cos phi. Cos phi is minus 1, right? So cos phi is minus 1. 9 over 2g into minus 1 is minus 9 over 2g, greater than 0. 3 over 4 u square is greater than 6. 15g over 2. Is that okay? 3g plus 9 over 2g. That's 15g over 2. So u square greater than 15g over 2 into 4 over 3. 2 times 1 is 2, 2 times 2 is 4, 3 times 1 is 3, 3 times 5 is 15. U square is greater than 5 times 2, 10g, right? Yeah. U square is greater than 10g. Okay, so u square. So basically u square is greater than 10g, which means u should be greater than root 10g. So this is the minimum. This is the minimum speed you require. Okay, so u should be greater than root 10g, and this is the requirement to perform a complete vertical circle. Okay. So I hope this part is clear with everyone. All right, guys, we'll move on to question number 10. A particle of mass 0.8 kilogram is attached to end A of a light rod AB of length 2 meters. The end B is attached to a fixed point so that the rod is free to rotate in a vertical circle with its center at B. The rod is held in a horizontal position and then released. Okay, so these are the initial things. First, you have the rod horizontal. Okay, so this is the point B. So this is the end of the rod, and at the end of the rod, you have the particle A. Okay. Okay. The length of the rod is 2 meters. Okay. So the rod is free to rotate in a vertical circle with its center at B. So the center is at B. The rod is held in a horizontal position and then released. Okay. So you keep the rod in a horizontal position and you release it. Calculate the speed of the particle and the tension in the rod when the particle is at the lowest point of the circle. So that of course is okay, right? So this is the lowest point. So when you're at the lowest point, okay, so what is the speed and the tension at the lowest point? Okay, at the lowest point of the circle. And then part B, calculate the speed and the tension when the rod makes an angle arc tan 3 over 4 with the downward vertical through B. Okay. All right. Okay. So we'll do the part A and B separately. I think part A should not be much of an issue, right? So that's quite easy. Okay, and then okay, so at this point you have to find the speed. So I will say that this point is V1. Okay, so first we have to get the speed and the tension at this point. So I will say this is the tension 1, and you have the weight. So weight is 0.8 G. Okay, so weight is 0.8 G. All right. All right, so we can first apply conservation of energy. So when you apply conservation of energy, so I will consider the downward position as the GP 0 level. Okay, so at the lower, at point A, initial energy, you can see, okay. So basically, that's in the rod is held in a horizontal position and then released. So I was just checking whether they have an initial speed. So there's no initial speed, okay, because they're just simply releasing. All right, so at this point, so all you have to do here is, let's apply the law of conservation of energy. At this point A, you have the mgh, the GPE, equal over here, you have half mv square. Okay, because at the point A, you don't have any speed. They say they're simply reducing it. So M cancels out. So G into height, guys, you can see very clearly height is the radius, the length of the rod, right? So height is 2 meters equals equals half into V square. So V square is what I'm trying to find. So V1, at this point, the speed is V1. So I get here V1 square is 4G. So V1 is root 4G. Guys, can you see? So V1 is root 4G, right? Okay, so you can get that value. So V1 is equal to root 4G is, how much is it? Root 4G. So that's 14 root 505, 6.26099. So basically 3SF, 6.26 meters per second. 3SF. All right. And then let's get the tension also. So we apply F equal MA towards the center. So towards center, I think you can see at the lowest point, center is directly upwards. Okay. So centripetal force, you have the tension P1 towards the center minus 0.8 G. Okay, because 0.8 G is acting away from the center. Equal mass into acceleration. Mass is 0.8 into centripetal acceleration V square over R. So T1 minus 0.8 G equals 0.8 into V square. I think you can see V1 is root 4G. So V1 square is 4G. Can you guys see? Please don't use 6.26 square. Okay, so it should be 4G square. I mean, use the exact figure. Over radius R is 2 meters. And guys, you can make P1 the subject now. So 0.8 into 4G over 2, 2 and 4 cancel, that's 2G, 2 into 0.8, that's 1.6G plus 0.8G. So T1, that's going to be, 2.4G, right? Is that okay? And then give the G value as 9.8. So 2.4 into 9.8 and give it to 3SF. 23.52. So correct to 3SF. 23.5 Newton, correct to 3SF. Okay, so this is the answer for part A. Okay, so moving on to part B, they say to calculate the speed of the particle and the tension in the rod when the rod makes an angle of arctan means tan inverse 3 over 4 with the downward vertical through B. Okay, so when you make an angle of arctan 3 over 4 with the downward vertical through B, so they are asking you what is the, basically the speed and the tension. Okay, so guys, the downward vertical, first thing you should know is the downward vertical. This is the downward vertical. So from B, directly below B is downward vertical. Directly above B, you have upward vertical. So that's the first thing you should know. Okay, so let me, I'll kind of like, erase this. Is that okay? I'll use the same diagram. Okay, so guys, this is the downward vertical. I'm going to do part B here. So this is what we call as downward vertical. So they are saying you to find the speed when the particle makes an angle of arctan 3 over 4 with the downward vertical. So let's say this is the particle now. And so this is the angle theta. Can you see? So this angle theta, they say the tan inverse. Angle theta is equal to tan inverse 3 over 4. Can you see? Which means in other words, the angle with the downward vertical is theta. That downward angle is tan inverse 3 over 4, which means tan theta is 3 over 4. Can you see, guys? Tan theta is 3 over 4. So using this information, you can find sine theta and cos theta. So tan theta opposite over adjacent. 3 over 4. Opposite is 3, adjacent. This is M1, right? Where you just have the ratio and you can use the Pythagoras theorem. You can calculate the hypotenuse 3 square plus 4 square square root. That's 5. And now you can get sine theta opposite over adjacent. Opposite is 3, adjacent is Opposite over hypotenuse, 3 over 5. Cos theta adjacent over hypotenuse, 4 over 5. Is that okay? And then what we do here is, guys, over here. So simply you need to again calculate the speed and the, you have to get the speed and the tension. So over here, this is V2. So let's say the speed is V2. So this is the tension T. I'll say the tension is T2. Weight is acting directly down. Okay, let me mark the weight first. Weight is acting directly down. Weight is, how much was the weight? 0.8. 0.8 G. Okay, so particle is going with speed V2. All right, so this is the diagram. So now for this diagram, you have to find the V2, the speed, and the tension, T2. Okay, so let's use the law of conservation of energy. Guys, by the way, this angle theta, if you wanted, you could have even made the theta angle to the other side. Okay, it won't make any difference, by the way. Okay, because some of you might be thinking, can't we take the angle to the downward vertical over here? Yes, you can use it like that. That's perfectly fine. If you want to use the theta angle over here to the other side and do, even that would be fine, because in circular motion, basically the vertical, the two sides, the vertical axis is like a line of symmetry, and on either side, when you achieve the same horizontal level, I think you can see the speeds, the tensions, they are all completely matching. Okay, so if you want, you could even consider like that. All right, so law of conservation of energy, I'll consider from A to this point. Okay, so at A, I have MGH. Okay, I'm considering the GP0 level down over here, MGH. And at B, so I have, let's say it's the initial potential energy. So at the point, at this particular point, guys, you can see over here, you are still above the ground level, right? So you still have a GP, because you're above the GP0 level. By the way, if you require, you can use this point as a GP0 level. That's perfectly fine. Okay, you can use this level as GP0 and take the GP from A to this point as the height. And for this point, you don't need to use a GP. Okay, that's perfectly fine. That's perfectly fine. Plus kinetic energy. Okay, so guys, I'll be measuring the height from the level ground. Okay, so actually, since I have marked it over here, GP0 level, that's why I'm marking it from this point. But if you want to take the GP0 level here and do it, that's perfectly okay. Okay, that's perfectly fine. Okay. So initial GPE, the height, I have to consider this full height, right? So full height mg height is 2 meters, because the length here, the radius is 2 meters. Final GP is also mgh. So guys, what about the height? So this is the height we need to consider now. Can you see? Okay, so this is the height we need to consider. So guys, you know this full length is 2 meters, right? Okay, so and you know that this is also 2 meters. So this length is 2 cos theta. Can you guys see? This length is 2 cos theta when you resolve towards the angle. So h will be 2 minus 2 cos theta. Can you see? This h will be from 2, you subtract 2 cos theta. Okay. All right. And then plus the kinetic energy, half mv2 square. Okay. So I use the speed here as v2. So guys, I hope you're following me. I can remove m from everyone. M is common. So I get over here 2g equals, I'll open the bracket here, 2g minus 2g cos theta plus half v2 square. You can see the 2g part cancels. That's the common height part. Okay, so anyway, this cancels. 2g plus 2g minus 2g. When you bring the 2g to the other side as a minus 2g, the plus 2g and the minus 2g will cancel out. Okay, when you bring it to the other side. So you can see here, I get 2g cos theta is equal to half V2 square. So I get here V2 square is equal to 4g cos theta. Can you see, guys? And cos theta value is known. Cos theta is 4/5. Input the value. 4g cos theta is 4/5 equals V2 square. So we get 16g/5 is equal to V2 square. Can you see? So 16g/5 is equal to V2 square. Right? So V2 is root 16g/5. So how much is it? 16 into 9.8 divided by 5. Square root the answer and you get 5.6, right? Directly. It's coming as an exact answer, 5.6 meters per second. Is that okay? Okay, and then after you come to that point, let's also get the tension. So we'll apply F equal ma towards center because we're supposed to find the tension. So guys, towards center, I think you can see at this point, towards center, always towards the B. Okay, so this is the towards center. You can see tension. You never have to worry about the tension. Tension is always directed towards the center. So over here, the weight is the issue because the line of action of the weight is not directed towards the center. So that is why weight needs to be resolved. Tension doesn't need to be resolved because the line of action of the tension is already directed towards the center. That's not an issue, but the weight is an issue and that needs to be resolved. So as I told you, the theta comes over here, right? This theta because of corresponding angles, and you get over here the resolving. (0.8g cos theta). 0.8g cos theta, right? So that's the factor I require. Okay, the theta came here through corresponding angle, 0.8g cos theta. So now we'll apply equal ma towards the center. So you can see T2 is towards the center minus 0.8g cos theta. T2 minus 0.8g cos theta equals ma. Mass into acceleration is v square over r. So T2 minus 0.8g cos theta equals mass 0.8. V square, guys, we just found the answer. I think we have the exact answer over here. So we can go with 5.6 because it's already exact. Or else we'll use, V2 square, right? So V2 square, we'll use V2 square, 16g/5. Okay, so this is V2 square over radius. I'll put the radius value over here. Divide by radius. Radius is 2 meters. All right, so T2 equals 0.8 into 16g over 2 times 510 plus 0.8g cos theta. Zero 0.8g cos theta is 4/5. Okay, so give the whole thing in the cal. G is 9.8, right? So give the G value as 9.8 and you should get the tension. So how much is it? T2 is the tension at that point. So we get, how much is it? Let's check it again. All right, yeah, so it's 18.816, right? Yeah. 18.8 Newtons. So this is corrected to 3 SI. 18.8 Newtons corrected to 3 SI. Okay, guys, so I hope you understood this section clearly now, right? So I think we'll do a few more questions, but at this point, I hope that I have made it clear until this question, okay? All right.